Hi everyone, let's work on some applications of the chain rule. So before I even get into that, I actually want to make sure that I show you the way that the chain rule looks in both function and dy dx notation. So we've already seen the function notation version. We know that the derivative of f of g of x is f prime evaluated at g of x multiplied by g prime of x. And we could even say, if we're interested in that, evaluated at a specific number. So if we want the derivative of f of g of x evaluated at x equals a, then it would be an f prime of g of a multiplied by g prime of a, and that might not look like anything too crazy that I'm saying, but this is the really important part. When you take the derivative of a composition, you get an f prime times a g prime, but it's really important to realize that if you start plugging in numbers, g prime will be evaluated at your x value, but f prime will not. F prime will be evaluated at g of your x value. So the thing you're plugging into f prime is not just a. Okay, so that's the same thing that's really important to realize with the other notation. So alternatively, I'm going to define some things. So let's say if, how did I do it? I'm going to follow my old one. If g of x is equal to z, so function g, inputs x's, outputs z's, and then we would need function f to input those z's, since we're trying to plug g of x into f. So g output a z, we plug that z into f, and then we finally get a y. So we are starting with x's and ending with y's, but there's this funny in-between variable. So we can say, using our dy dx type notation, if we want the derivative of y with respect to x, so the derivative of function f, but with respect to this variable way over here, then what we would do is we would take the derivative of function f, so the derivative of y with respect to its actual variable, z, and notice z is g of x's, so the derivative of y with respect to g of x, not just x, and then we would multiply by the derivative of g, so that's going to be, g was called z's, and that's with respect to x. And this just might look like I'm adding an extra layer of confusion for you, but there's some things I really like about this. One is that it does emphasize the slope relationship. So if you want to find dy dx, that's change in y over change in x. It is an infinitely small change in y and change in x, but that reminds me a lot of slope. And same thing here. It says you take change in y over change in z and multiply it by change in z over change in x, so slope and slope. And then the other thing I like is it looks like fraction arithmetic, so you can tell if you got it set up the right way or not. So the dz's look like they should just cancel, and then we get dy dx equals dy dx. Okay, so this is fabulous, but again, what I really want to focus on a little bit is, for the sake of word problems, how does this look if you're trying to evaluate at x equals a? So this is supposed to be the derivative of y with respect to x. I should evaluate at some given x value. But the way that looks is, part of it's easy. dz dx is a function of x, so it should get evaluated at x equals a as well. But dy dz needs to get a z value plugged in, not an x value. So if we know an x value and we want a z value, we would plug that x value into function g. So it's just like before. But again, I kind of like the way this one looks, that it looks like fraction arithmetic, and it reminds me of slopes, and I like to use either one, but I do like to use the second one for word problems. Okay, so with this extra little bit of notation in mind, I would like to work through an application. Okay, so my application, I got my cheat sheet here so I don't have to calculator on you along the way, is that I have these two functions. So first I have function p of t, and it is, let me remind myself, it is inputting the number of years since 1995 and outputting the population of a city in thousands. And then I have this function g of p, that inputs population in thousands and outputs number of garbage trucks needed by this city. Okay, so I want to go through and I want to find the value of each thing, I have A through E here, in 2010. Okay, so if I want to figure out the value of P of T in 2010, that means I should find the population in 2010. So that's fairly easy because P actually inputs time in years. So I really just have to figure out, if I'm starting in 1995, what is T going to be? So it looks like it's going to be 15. So here I really want to find P of 15. And this just becomes a calculator problem. So you plug in here, hopefully very carefully. If you want to test your calculator skills, go for it. What I got was 13.144. And I don't mind if you don't keep the extra decimal place. I was just thinking, if this is in thousands, so this is the answer to the question. But if I was going to try and explain what this is telling me, it's telling me that in 2010, the population was 13,144 people. So again, I'm fine. I don't really bug you about significant figures or anything, but probably we don't expect this thing to be this accurate anyway. So if you round it and you say this is 13,140, totally fine. Okay, so there is the value of P, the population in 2010. G of P, so G outputs number of garbage trucks. So now I'm supposed to figure out how many garbage trucks we needed in 2010. But this is a little tricky because G doesn't input a time. G inputs a population. So actually we get off easy because we've just done some of this work, but that's the really important thing to realize. It would not make sense to plug 15 in here because G inputs population. So really we would first want to say that P of 15 is about 13.144. And then we could say G of 13.144. And again, this becomes a not super exciting calculator problem. Ooh, I'm peeking. I scratched something out. Hopefully I'm trustworthy. It looks like I decided after 2 tries that this was about 24.017. So what this is telling me is that in 2010, the city needed about 24 garbage trucks. Or if you want to round up, it's pretty darn close to 24, but if you want to say, well, that won't quite get the job done, I need 25, fine, just make sure I can see this number so I know what you are working from. Okay, and now into the derivative. So I want to figure out the value of dp dt in 2010. So first I need to find a formula for dp dt. So I'm looking way back up here at this function, and it looks to me like, is there any sneaky way to do it? It looks to me like I probably want a quotient rule. So I'm going to say I want the bottom 1 plus 12 e to the negative 0.02t multiplied by the derivative of the top, which is actually 0, so that makes that kind of easy. And that is symptomatic of the fact that you could, if you wanted to, rewrite this as 130 times 1 plus 12e to the negative 0.02t, all raised to the negative 1. I don't know that that makes it easier or not easier because now you have an extra chain, but it is something that you could do. Okay, so then, where was I at? So that was the bottom derivative of the top, and then I want minus the top times the derivative of the bottom. So the 1 is just going to go away, derivative of 1 is 0. The 12 is going to come along for the ride. The derivative of e to the stuff is e to the stuff. And then the last step here, since that wasn't just e to the t, it was e to the stuff, I will have to do a chain rule and say I need to multiply by the derivative of the stuff, which is negative 0.02. And then all of this should get divided by the bottom squared. So it's going to be a 1 plus 12 e to the negative 0.02t squared. Okay, so all this is actually gone. And we end up with just that mess. And since our question wasn't really what is the derivative, but what's the value of the derivative in 2010, I'm not super worried about writing out the simplification. But you can if you want to. There is one nice thing that happens. Those minus signs go away. And if you wanted, you could multiply the 12 and the 130 and the 0.02 to make the top a little cleaner. When I plugged all this mess in, so if we want dp dt evaluated when t equals 15, that gives us 2010. Where did it go? I got about 0.236. Okay, which that's the answer to what is the value of dp dt in 2010. If we want to talk about what that means, that's a slope, change in p over change in t, change in population over change in time. So it's going to be population increases by 0.236 thousand every year. 0.236 thousand is 236, so this is 236. It's increased by 236 people per year. So it didn't ask for the interpretation, but I want to make sure we're keeping track of that. Okay, and then we are supposed to try and find the value of dg/dp in 2010. And once again, this is the one to pay attention to. I'm being asked for information about 2010, but this is not actually a function of time. So I can find a formula for dg/dp. It's not actually too messy. Derivative of 2p is just 2. And then we have a subtraction. The derivative of 0.001p cubed is 0.003p squared. If we want to figure out the value of this thing in 2010, notice this is a function of p, so we would have to plug in the population in 2010. So this is going to be when p equals, or is approximately equal to 13.144. Back to that thing we found at the very beginning. Sorry if you couldn't see that. And when I did that, I got about 1.48. So this, again, there's your answer, but I do want to talk about what it means. This is telling me change in G over change in P. So this is change in garbage trucks over change in population. So this says that we need an additional about 1.5 for every 1,000 people. So if there's 1,000 more people in the population, we need about 1.5 more trucks, or you could say for every 2,000 people, we need 3 more trucks. All right, last one. This is kind of the grand finale, but it doesn't seem that impressive because we've actually already done all the work. But this is about, okay, well, what if I don't want to know how fast the number of garbage truck needs, I can't speak. What if I don't want to know about how fast the number of garbage trucks needed is increasing with respect to people, but instead with respect to time, so that I can say, okay, in 5 years I'm going to need this many more garbage trucks. And the answer is, if we want to find dg/dt, we need to find dg/dp and multiply it by dp/dt. There's 2 steps involved there because there's a composition between variables g and variables t. And then again, the thing that gets a little bit tricky is we want to know about this when t equals 15. So we're going to evaluate dp/dt when t equals 15. But we can't just straight up plug 15 into dg/dp because that is not a function of time. So we have to plug in the appropriate p-value. So the p-value that matches with the population that matches with 2010, which is that 13.144, if you can see that snuck in there. Okay, again, this is kind of anticlimactic because we walked through and we actually did all this work. So what we need to do is take the 1.48, and I actually think the units are really helpful here. Trucks, not tucks. Tucks per 1,000 people. And then we're going to multiply it by our 0.236. I guess writing out that 1,000 was probably bad. Let's write it in words. 1,000 people per year. And what happens is we lose the thousands of people units, and we just end up with trucks per year. And it's this 1.48 multiplied by 0.236, which is about, and this was really approximate as well, 0.349 trucks per year. And again, if you want to, so it's about a third of a truck per year. If you want to say roughly one truck every 3 years, that's fine. I am okay with the decimal here. It's a rate of increase, so I think that's okay. All right, thanks for watching.